Okay, so we'll start again. So we have Misha Gekhtman again, talking about total positivity in directed networks.
Right. Thank you. We talked quite a bit about total positivity yesterday, and today we're going to segue to directed networks. The way to get to directed networks will be to talk about criteria for total positivity. We talked yesterday about how the number of minors, if you want to check all of them, grows exponentially, and you want to find a minimal amount of minors or some other quantities to check for total positivity. We also saw an example yesterday that even though if you just have a positive matrix and 2 by 2 minors, well, there is a lot of them, more than n squared, but their positivity is not enough. So I wanted to talk about first some nice sufficient condition for total positivity, which is relatively recent. So this is work of Kharkiv mathematicians Katkova and Vishnyakova from 2006. What this condition is about is strengthening 2 by 2 minor positivity. So we know that in general, total positivity in particular implies that if you have a matrix A and you take any entry ij and consider this dense 2 by 2 minor, so I'm just looking at dense 2 by 2 minors, right? So the consecutive rows and columns, it has to be positive. Now, you can write it as an inequality, of course, of the form aij, ai plus 1, j plus 1 is greater than ai plus 1, j and j plus 1. And what you may want to do is to strengthen the condition of positivity of the determinant by just putting here some constant c, where c is greater than 1. So when c is equal to 1, this is the same condition, but you want to put some other constant c, which is greater than 1. And the question is, maybe this will be enough for complete total positivity. And so there is this nice theorem. So let's call this condition star. So if A is n by n, entry-wise positive, and such that star is satisfied with c equals 4 cosine squared pi over n plus 1, then A is totally positive. So it's a very nice result, rather unexpected, and moreover, this value is optimal. Right? So the proof is long, it's elementary, but very clever, using Chebyshev polynomials and some other techniques, but maybe I can at least briefly sketch the reasons why it is optimal. because it will bring us again to tri-diagonal or Jacobi matrices that were featured in also in Professor Tsuzumoto's lectures. So, and I will phrase it as exercises, even there are no more problem sessions. Yes.
I have a comment to make that 4 reminds me of a theorem that is maybe not very well known. So if you have a univariate polynomial with real coefficients, then we know that this thing, the Newton inequalities hold. So AI square is bigger than AI plus 1, AI minus 1.
Right.
But if you have the condition that AI square is bigger than 4 times AI plus 1, AI minus 1, then that's a sufficient condition for real rootedness.
Right. So yeah. So there is a relation there, in fact. So yes, there is a property of polynomials where you build such inequalities with coefficients, and you can build this into matrices like the Hurwitz matrix that we talked about yesterday. Yeah, but this is a very good comment. So so optimality. So what you do is you consider a matrix, let's call it AN of theta, which looks like a truncated recurrence matrix for Chebyshev polynomials. Instead, so in Chebyshev polynomials, you'll have zeros on the diagonal. Instead, here, you put cosine 2 theta everywhere on their diagonal. Right? So let's just consider this tri-diagonal matrix. And cosine 2 theta. Cosine 2 theta. So you have this nested family of matrices, and one can do so, steps in the proof of optimality, one can do the following. First of all, there is a nice recurrence for determinants of AN theta. It's easy to obtain just by Laplace expanding, which leads to explicit formula for that. And that is simply sine n plus 1 theta over sine theta. All right? And from that, you can then derive the following. This is step 3, and I leave the... Exactly, yeah. And from, so step 3 then that if C is less than 4 cosine square pi n plus 1, then one can find theta such that star is satisfied with that C, but the determinant of AN theta is less than 0, and this is all you need to do. So it boils down to just simple trigonometry. Right, so you can figure out where to look for such theta. So this is kind of half exercise. So the other direction is quite involved. So that's the result I wanted to mention. But now let's talk about actual criteria of total positivity. And for criteria of total positivity or total non-negativity can be derived from looking at planar weighted directed networks. And so this is due to first, a work of in different combinations, Bernstein, Famin, and Zelevinsky. So first, all three of them work it out for triangular matrices in just usual triangular matrices in GLN, but then Fomin and Zelevinsky extended this to the theory of total positivity on double Brouillard cells for other types. But we will stay within just n by n matrices. Yes.
Sorry, just to clarify, when you say we can find theta such that star is satisfied for
So if
AN,
C is less than this number,
but star is satisfied for this AN, right?
for this, yeah, so the star is satisfied for this. Yeah, thank you. Yeah. All right. So now we'll just have to try to replace matrices with pictures. Okay. And so the idea is the following. So we'll start. So we already know that tridiagonal matrices play a role in total positivity, that tridiagonal matrices can be factored into bidiagonal matrices, but they can be factored even further. So I'm going to start with pictures representing the following matrices. So first, let's consider a matrix E, I of T. This is n by n matrix of the form 1 plus T I plus 1. So I'll try to stick with this notation. I'll hang a plus over here. Then we can consider matrix EI minus of T, which will be 1 plus T I plus 1 E I plus 1 I. And this is just elementary matrices with 1 in this place and 0 everywhere else. And then D will be just a diagonal of D1 and so on Dn. And we can represent these matrices with pictures. So I will first do this diagrammatic representation for these matrices, and then we will glue them together into something more complicated. So I'll do it in some example. So what you start with, you draw kind of rails. So in this case, I is going to be equals 82. And then you imagine that there is a flow from left to right. And then you draw an inclined edge to emphasize that it's from left to right and put a weight T over here. All right? So similarly here, you have 1. So let me now write it like this, 1 through n. 1 through n, there is I plus 1 here, and there is T over here. And this one is even simpler. You have, again, 1, n, 1, n, d1, d2, and so on, dn. And so this is E2, but yeah, well, yeah. But you can easily generalize it. And so, okay, so you can describe all of them, all of these matrices by the following rule. So I have edges here. Some of them have weight attached to them. If the weight is not attached to an edge, we'll say that weight is equal to 1. This is our convention. And all of these matrices are very simple, but they can be described in the following way. So we have a matrix A associated with a network N, like of this sort, where you have N sources on the left and things on the right, and then you have some edges, inclined edges, inclined this direction and that direction. It always goes from left to right with some weights. I'm not going to write the weights. And then to find this matrix, what you do, you say that ij entry of this matrix is simply a sum over all paths in my network that lead from I to J, so path, of product of weights along the path. All right? So it's very easy to see that these three matrices conform to this definition. All right? So this one is almost diagonal. There is just one, yeah. So there is just one path from 2 to 3, and it will have weight t, and this is what we have here. All right?
So the ordering of the edges also matters?
Yeah, well, it will matter in the result, but for now, I allow any edges being in any order. I can still define a matrix this way. Yeah. And then you can use these things as building blocks, and then you can just say these magic words. So this is our mantra. Concatenation equals multiplication. Right? So what happens if I have two networks? It doesn't matter what's in here. So if I have matrix A, matrix B, I want to multiply them, and I want to consider element ij. So here's I, here somewhere is j. And what do? I sum all aik's times all kj's, right? So I will consider all the passes that lead me here, and then all the passes that lead me here. And if k varies, I will get all the passes that lead from I to j in the product. So it's exactly the same as matrix multiplication. So by using this property, I can glue together as many as I want of these elementary matrices. So I can do something more complicated, but for now, I don't need to. But there are even nicer properties. So is it clear what I'm doing? So any network can be obtained this way. So I can glue them together, or if I have a network, I can cut it in these elementary pieces. And then there is this theorem, which is called, well, by many names, and I don't know in which order to put them, so I'll just put them in alphabetical order, which will make no sense whatsoever, because two co-authors will be interspersed by a third independent name, but well, the other people work on that. I think it goes back to Cardin and McGregor. In fact, this is the lemma. So if you have A that corresponds to a network N, and we want to compute a determinant of A with row set I and the minor and column set J, then what you need to do is consider a sum. So I have this I as I1 through K, J1 through JK, and then we consider only non-crossing path, right? So we consider family of all non-crossing paths from index set I to index set J. And then you consider again product of weights along the path, and that's it. All right? So it's very clear what's nice about this formula and why it's very appropriate for the study of total positivity. There are no minus signs here. There are several proofs, and yeah, you can leave it as an exercise. The simplest proof is the following. If I have any network at all, I can cut it into simple pieces like we have over there. It's clear how to compute determinant for these ones. and then use Binet-Cauchy theorem, which does not contain any minus sign. So that's how you can prove. All right, so is it clear? So one immediate implication of this is...
Can I ask? I'm a bit confused about one point. So if I have a generic diagram, if these slanting edges are at general position, I can always cut them up into elementary things. But suppose they are exactly one on top of the other, then
well, so these diagrams, that's a good question. So let me give you an example of that. So this is Arvind's question. So what if I have, and you will see these things, so one on top of another. Well, no one prevents you from cutting it like this, right? It doesn't matter. It's so as long as they don't change the ordering, we can move them whichever way we want. Exactly. In fact, sometimes you will see examples that are very convenient to draw these networks, not the way I presented them, but just move them around. So, right. So, immediate consequence of this, or corollary of this lemma, if all the weights are positive, that means that corresponding matrix A that comes from the network is totally non-negative. It's not necessarily totally positive because we may not have even a single collection of non-intersecting paths. But everything here will be positive, so if we do have at least one collection, then it will produce a totally non-negative matrix. But in fact, there is a converse statement which is true. So here's another claim, which I will explain an example, which can be easily scaled to a general proof. So any TP matrix can be represented by a network with exactly n square positive independent parameters. So there could be some weights there which are equal to 1, but you can select it in such a way. And there is a very organized way to do it, which is part of this work of Bernstein, Fomin, and Zelevinsky. But I will consider an example to see how it works and how you can actually derive from that criteria of total positivity and then and even more. So let's just do 3 by 3 examples. This should be enough to understand what's going on. So I'm going to draw this network. It's one of the preferred networks, but we'll see that it's not unique for our purposes. And I will put weights here, so this will be lower L1, L2, L3, and then we have D1, D2, D3, and then you have U1, U2, U3. Okay, so again, if I have all of these guys positive, then the result is totally positive. Why is it totally positive? Because you can easily check. So if you take select any subset of indices, you can draw at least one non-intersecting collection of paths. All right, but sometimes you'll have more. So what I want to do now is list all the minors of the resulting matrix. So I'm going just to be informal and write that this is equal to A. So I want to find a selection of minors which correspond to just a single collection of non-intersecting paths. And then the resulting expressions in terms of the thing will be monomial. Okay? So, and this will be like a joint exercise for us. So for example, A11 is equal D1. There is only one way to get from here to there. Because we're just moving from left to right, there is no turning back. So if I turn up, then I will never come back. Now I'll stop writing that and just write corresponding submetrics. A1212 is equal to D1, D2. And then, well, determinant of A is equal to D1, D2, D3. Okay? I want to say that right away from this, let me just notice something, that from this I can, if I know A, and I know that A is represented by such a metric, such a network, I can immediately restore D1, and then D2, and then D3. Then I'll have A32 is equal L2, D2, and A23 is equal D2, U2. Okay? So let's do 2, 3. Oh, no, sorry. No. I can go down. Thank you. I'm going to correct this. Yeah, so let's go with the obvious one first. So A31 is L2, L3, D1. A13 is D1, U1, U2, okay? Then we have A2, 3, 1, 2. So let me just give one example of that. So I'm going from here, from this two to this two. So I have to go down from here to here, and then immediately I'll get only one collection of paths. Right? So that will be L1, L2, D1, D2. The picture is symmetric. A1, 1, 2, 2, 3 is going to be D1, D2, U2, U3. So how many functions I have? 1, 2, 3, 4, 5, 6, 7. And with your help, I'll find 2 more. Because I was just corrected, I'm going to write now that A1312. So I was corrected by Philippe that I can go down and up again. But now if I add 1, 1, and then 3, 2, I can no longer go down. I cut it off because I need non-intersecting paths. So I'll have now L2, sorry, D1, D2, and since the picture is symmetric, then what is it, the other way around, 1, 2, 1, 3, is going to be D1, U2. Okay, so why do I stop here? Because I'm looking to restore 9 parameters, and I have 9 functions here. And what you will observe now, so instead of writing formulas, I will start just underline what I can restore. So I restored D1, D2, D3. Because I did that, I can now restore U2 and, oh, sorry, D1, D2 here, but it doesn't matter. U2 and L2. Now I know L2, D1, D2, I can restore L1. Now I know L1, L2, I can restore L3. And so everything is restored. And it's restored in a monomial way from this collection of minors, okay? So what does it tell me? If I have a totally positive matrix, I can restore all these weights, and they all will be positive, okay? So there is this one-to-one correspondence between totally positive matrices and networks of this shape, okay? And you can, again, you can easily extend it to a more to larger dimensions. Now let's see what's actually going on here combinatorially. So to do that, I'm sorry, there will be a lot of colors in this picture. So I'm going to look at these inclined edges and see where these edges end, right? Or well, the low. I just mark the low part of this edge. So here, this one ends at 1, level 1. This ends at level 2, level 1. And the same here. Starts at 1, 2, 1. So this should remind us of something. So let me just write the following expression. S1, S2, S1 is equal W0, the longest permutation in S3. Okay? And then, well, you may ask me, what do I do if, well, this is not the only presentation of the longest permutation in S3, so let's just try to do that. And I'll stop writing weights momentarily. So if I do S2, S1, S2, then that's what's going to happen here. Okay? But the same story will remain true, except that now I cannot use. So I'm saying that in this collection of minors, one of them will stop being a monomial. So A1312, A1312 is no longer will be monomial because now I can get, in two ways, here and here. So
1, 3, 2, 3.
yeah. So now, yeah. So I have to replace it with something, and this something could be, well, could be several things. In fact, but for example, I can do a 1, 2, 1, 3, 1, 2, and well, replace it with several things. So the simplest one will be simply A 2, 1, and there is only one way to get here. Okay? So, and this is important because there is a collection of 9 functions which actually form coordinates on totally positive matrices, and then we replaced one of them with something else, and you will probably believe me when I'll tell you that you can express this something else through the rest of them using determinantal formulas, and that will be an example of cluster transformation, which I will write down later. So now we can formulate a general. Yeah, this is entry of. Yeah, of the same matrix. Yeah. So now we can formulate this general result of Bernstein from Lewinsky, which actually works for all reductive groups.
Sorry, so before you go there, I'm a bit confused about the connection with the long word. So I understand that this is 1, 2, and 1.
Yeah.
But that does not seem to be, I mean, if I do those transpositions here, I mean, it's not like 2 is going back to 2, right? Because 2 goes down to 1 and stays at 1.
Yeah. No. So the word is obtained as the following. So you consider all southeast edges, and just record in order at which level they end. 1, 2, 1.
Yeah, I understand that. But why I don't see the connection to the long word, because it's not like 1, 2, 3 becomes 3, 2, 1, right? Because
no, it's the same. It's the same long word. It's just different. It's a different reduced word for the longest permutation.
I understand what you're trying to say, but I'm not seeing. 1 does not. I mean, I can see that 3 goes down to 1 using L2 and L3, but 1 does not go up to 3, right?
You would like to see the permutation.
I thought you would. How would I see the connection to the long word? I mean, So from 3, if you start, you use L2 and L3 to come down to 1.
Right.
But from 1, you cannot go up to 3.
Again? Over
No,
here.
but there, but
Oh, no, but here you should not go up to 3. This represents a triangular matrix.
okay.
Yeah,
So I have to use both sides.
Yeah, exactly. Yeah. So I'm just saying that I can, in particular, replace things here, use a different word here.
Oh, you can use.
Yeah, and I can use different word here. And in fact, I'm going to write exactly what I'm allowed to use. So that's a theorem which states the following. So suppose we have 2 reduced words for W0. One is I1, I2, so L, where L is n-1/2. This is the length of the longest word. Or you can do J1, J2, and so on, JL. Okay? And so you have 2 reduced words. And then you take these 2 words and then consider an arbitrary shuffle of these words. Let's call them I and J. Okay? And so shuffle means that I take this word and then stuck the other word in between indices here. So arbitrary shuffle. And then consider the following map. So there is a map R n squared, which can be written as Rn times RL times RL. Okay? And this maps us into GLN. Okay? And how does it work? So here I have D1, Dn parameters. Here I have, let's call them, let's not use L any longer, so I'll call them T1, TL plus, and here T1, TL minus. Okay? And so let's call this shuffle K. So I have a shuffle of those. Okay? And then the map is the following. So the matrix I'm going to construct is the following. It's a diagonal D1, Dn. And then, so let me just say what will happen inside the word. So I'm reading this word, K, and if I see index from the first word, I will write down E plus I, whatever, S of T S. And if I have encounter within this somebody from J, I'll see E minus J, I don't know, Q of T Q. Okay? So again, the word tells me whether to use plus or minus. And then I put the diagonal here, but I can also, well, it's easy to understand that the diagonal can be put anywhere. You can by commuting, you can put in appropriate way, put diagonal anywhere over here.
The arguments are T plus and T minus, right?
T is also a superscript.
Yeah, plus T minus. Thank you. Yeah. Okay. So I have this map.
Sorry, could you repeat the algorithm?
Yeah. So yeah.
What is R to the n doing?
R to the n is responsible for the diagonal part, and then this one is responsible for all the weights of edges that are going northeast, and this RL is responsible for all the edges that are going southeast. Okay? Okay, so I have this map. And, well.
So I didn't understand the math. So I first fill in all the diagonals.
Yeah. Yeah. So yeah. And then you go along this. Go along this word, and depending on whether entries in this word come from vector I, vector j, you do this. Okay. So this is a map, and actually, so the conclusion of the theorem, let's call it, I don't know, map rho. So rho is a diffeomorphism from, sorry, I should have, since I want to talk about total positivity, I'll define it on R plus. From R plus n square to the totally positive part, let me put it like this, of GLA. In other words, for any such selection of words in a shuffle, I can parameterize every single totally positive matrix by such a map, or equivalently by such a diagram. Okay, so let me do another example again for SL3. Sorry.
And here you really mean totally positive.
Total positivity, yeah. Here's total positivity. Yeah, so let me do an example for SL3. So let's say I1, I2, I1 is 1 to 1, J1, J2, J3 is 2, 1, 2. So to distinguish them, I'll just circle them like this. And then we have the following shuffle. Let's say 1, 2, 2, 1, 1, and 2. Okay? And so I'm going just to draw a corresponding diagram according to our rules. So 1 was for pluses. So in fact, I'll have 1, 2, 2, 1, and then another 1, and then another 2. This is where I put the weights. So T1 plus, T2 plus, T3 plus, T1 minus, T2 minus, T3 minus.
So GL plus is totally positive?
Totally positive part, yeah. And then I said that D1, D2, D3 have to be in the beginning, but in fact it's easy to see that I can put them anywhere on the corresponding horizontal level. So according to the theorem, it's D1, D2, D3, but you can pass them through any inclined wedge using so-called gauge transformation, which I will again remind in a moment. All right. So we obtained not just one, but many parameterizations of totally positive matrices.
So when you say you can pass them, they can be at different locations each?
Yes. So let me just do it here as an example. So suppose I want to put D1 over here. So I'm saying that nothing will change in the resulting matrix if I divide the weight of this edge by something and then multiply the edge, the incoming edges from the same vertex by the same something. So that means that if I replace here D1 with 1, then I have to put D1 over here and D1 over here. Okay. So this and this is just one of many transformations of weights, and this is a good question because, well, I want to describe some others. So transformations of networks. It is easy to see that I can pass from one of these pictures to another just by switching the order of edges by preserving their total number in structure. So there are several transformations that I can do to networks, but I also am forced to do something to the weights if I want them to represent the same matrix. So the most important, well, let's start with easy ones. So if somewhere in my network I have something like this, A and B and nothing in between, I don't need these two edges because it is equivalent to just A plus B. Right? Because there are two paths here, nothing interferes with it.
Assuming there's nothing in between.
Nothing in between, yeah. So this is an easy one. Another easy one is like this. If I have in my picture something of this sort, A and B, so if you ever multiplied matrices, you were happy to see this property, that it is the same thing as B and A switching like that. So those are easy ones, and then we have important ones. And important ones are so-called three-move. Okay, so I'll just write one version of it, but there is a symbol. So there's a low triangular version, but there is a upper triangular version as well. If I have here T1, T2, T3, it is equal to, so yeah, we know actually, so what it relates to, any two reduced words can be moved one into each other using three moves. So what it relates to is T2, T3 over T1 plus T3, T1 plus T3, T1, T2 over T1 plus T3. This is three move. So you can easily check that if this is just my entire matrix, then right and left sides represent the same matrix. And since these things are done locally, if we do them, nothing will happen to our result. And then there is a famous square move, also known as in various, so it's maybe spider move, urban renewal, and so on. There are many names. What it is in reality is just refactorization over 2x2 matrix, but let's try to write this one. So here I'll have A, B, C, D, and it is equal to, okay, so I want to switch the order of these edges, and I'll need some room for that. So I'm going to write the following. So over here, I'll have A, B, C plus D. Over here, I'll have, okay, so let's just denote this A, B, C plus D by, let's say, W. And then over here, I will have BD over W and BC over W and AB over W. That's a square move. Yes.
Sorry, just to clarify, what is the denominator on the first thing on the line?
T1 plus T3.
And it's the same?
It's the same, yeah.
Oh, and bottom is T1 plus T3 or T2?
T1 plus, sorry, it's T1 plus T3. My 3s and 2s look the same. So let's just check our sanity here. So here, to get from here to here, you'll get T2, T3. And here you also get T2, T3. So that's the way, actually, better than memorize this formula, it's worth it just to do it every time. All right? So one important property of all these transformations, we're talking about total positivity. There are no negative signs. Okay? All right. Yes?
Is swapped.
Sorry?
BC over W and AB over W is swapped in the spider move.
AB Sorry. You mean that I switched CN? Yeah, thank you. Yeah, so that's the danger of doing this on this one. All right, so yes, yeah, it took me quite a bit to do this, but
sorry, I missed something. What is W?
W, sorry, I just erased it. It's W is ABC plus D.
There's no parenthesis.
ABC plus D. Yeah. Yeah, well, again, why? Because on the left, to get from here to here, I can go along this line, which gives me D or ABC. All right. Okay, so that's parameterization of total positivity in terms of networks. So again, all this moves. So if you have a matrix, you have one network, and then you can get to another network using these transformations, but it will give you the same matrix. So there is no dynamics. Eventually, we want to get to some dynamics, but here it's not a dynamic. It's just different changes of coordinates, if you wish. But what I wanted to comment on, so this is all about total positivity, but in fact, you can use this picture to represent a lot of classes of matrices that we already talked about here. So what did we talk about? We talked about Jacobi matrices, we talked about Hankel matrices, we'll see elementary, we'll see some, but we'll see elementary Toda orbits, and all of them can be now represented by pictures. So, and then we talked also about, say, Pascal triangles, so we'll do that with pictures as well. So let's look at examples of C and N matrices through diagrams. Okay, so let's start with Jacobi. Okay, I'm not going to write weights. I'm not going to write indices. That's a Jacobi matrix. This, you know, you can, depending on the season, it can be Jacobi matrix like this, or it could be, you know, New Year. It's the same Jacobi matrix, right? So, well, there are more general things. So remember, we talked about how you may have some hidden zeros in your total and the negative matrix. So let me draw the following diagram. So now I'm going to do the following. So the same number of parameters, okay? But this will be a full matrix. This will be a full matrix, but I'm going to say that, you can see this by counting paths, that in this matrix, every minor 2 by 2 and up, which is strictly below and strictly above the diagonal, is 0. So in this picture, we have a lot of 0 elements. In this picture, we have a lot of 0 minors. Okay? And in fact, you can also see that this diagram is kind of inverse to this diagram because it's in opposite order. So if I put here weights and put here weights and here put the same weights but with negative signs, this is exactly the inverse. So you can and a positive inverse when you ignore the sign. What kind of matrix is this? This is where, in terms of integrable system, where the Picon lattice lives. And now you can combine them in any way. So let me just say it in words. If you have exactly one inclined edge in both directions at each level, then the corresponding set of matrices is called a Coxter double Brouwer cell, because the corresponding, if you write down elements like of our permutation group, so it will be S1, sorry, here is S3, S2, S1, here it will be S1, S2, S3. So those are Coxter elements in the permutation group. And for any pair of Coxter elements, you can draw such a diagram, and Toda flows will restrict to to this, and we'll talk about this later. What else can we do? We can do a Hankel matrix. If I have, yeah, I have time for Hankel matrix. So this is very nice too. So Hankel. This is what I'm going to do. So now, suppose I have some diagram for some matrix. Let it be Jacobian matrix because there is a relevance there. So I will just have some big diagram for my Jacobian matrix, and then I can replicate this diagram. Replicate in both directions as many times as I want, okay? And I'm going to produce another matrix out of that. So now, this is, I said that these diagrams can be represented in different ways. So incoming edges will be here, 1, 2, 3. Outgoing will be here, 1, 2, 3, and so on. And I want to write a corresponding matrix corresponding to this diagram. So it's now. So I just repeat this, but it's an infinite matrix. It's an infinite strip, but I have only finitely many of sources and things. And you can see that there is a certain symmetry here, right? So if I start from 2 and get here at 1, it's the same thing as 1 and get a 2. So what is this? What's the corresponding matrix? Corresponding matrix is H of the form. So let me put H0 here just for consistency. So H0, H1, H1, we will have this Hankel structure, and so on. And what are those HKs? HKs, if you think about it, what are they?
Sorry, I didn't understand what you mean by adding these sources and sinks.
So in my diagrams, I have sources and things, and things, right? So I can place them in my picture where it is convenient. And so for this particular picture, I say that I place all the sources. So this is the continuation of my diagram.
So you don't have a requirement that they be planar, these diagrams?
It is planar. It is still planar because if I can draw it in the same way I draw it here, but it will be very ugly looking because I have to squish all of these J's, but it's still planar.
But I thought since you were concatenating all these J diagrams that on the left you had all these sources already, no?
Well, yeah, so I concatenated them, they stopped being sources of things, and then I have to replace with some other sources of things.
Is it possible to draw a small example?
Yeah.
Are you concatenating infinitely many of them?
Yeah, infinitely many, but I can choose then just finitely many of this sources. Let me. I think small example will probably confuse things. Yeah. So let me do it over here. Yeah, I'll do the same two things. Yeah. So here will be an example, just two of them. So 1, 2. So I'm repeating the same thing. Okay, and then I'm coming here, going here. This is 1, 1, and this is 2, and this is 2. Okay. And so what will be the two?
Yeah. Have to connect to line number 2?
Yeah.
Because you connected source number 2 to the first line?
Source number 2. No, it's all connected to the bottom line.
Ah, okay.
It's all connected to the bottom line. And then, so what will be, so this entry will give, this 1, 1 will be just 1. Okay, 1, 2, so what do? I go here, and then I'm in my old diagram, it will give me J, 1, 1. And then 2, 1 will also give me J, 1, 1. And then 2, 2, so I'm incoming here, And it will be give me what? So I have j and then go here. So it will be j square 1, 1. So this Hankel matrix will be made out of j to the power, so this is j to the power k, element 1, 1. And those are called moments of corresponding Jacobi matrix. And you can use this to solve moment problem combinatorially. So Hankel matrices are like that. So maybe let me do Pascal just for completeness. So we talked about positivity of the binomial, total positivity of binomial coefficients. And again, I'm going to arrange things in a way that is convenient for me. So let me draw now just a square lattice, no weights whatsoever. Okay, and then I'll have, again, 1, it's still planar, 2, 2, 3, 3, and so on, right? 4, 4, and well, what are going to be, so, and all the weights are equal to 1, and all the arrows are pointing in this direction, So what is the corresponding matrix? Well, we'll just have to count the paths from bottom to the right, and so the corresponding matrix will be, okay, I hope I will not make a mistake here, I plus j minus 2, and here will be I minus 1, ij from 1 to, well, in this case, to infinity. So this will be a matrix of binomial coefficients, okay? And right away, you see something nice, which you can obtain without doing any computations. So if you consider matrix of binomial coefficients, take huge square submatrix that sits in the upper left corner. The determinant of that thing is equal to 1. Why is it equal to 1? Because there is only one way to construct a non-intersecting family of paths. All right? So, sorry, I think I'm running behind, but I'll stop here. So I promised to say something about spectral properties, but I'll say it later. Yeah.
Thank you. So we have a little bit of time for questions.
Yes.
So you have some correspondence between these directed networks and diamond models.
Yeah.
So for square move, I see what the analog move would be for the diamond model, but for the 3 move, is there an analog?
I think there is a way to obtain it through a combination of several square moves. So yeah, there is. Yeah.
But so in that case, do you need the 3 move as a basic move?
Well, it's just easier to illustrate. Yeah.
Actually, doesn't free move correspond more or less to Young-Baxter?
Yeah, it corresponds to Young-Baxter too, but I think both are true at the same time. Yeah, also 3 move is nice because it has analogs for other Lie types. It just becomes, for CD F types, it becomes 4 move, and for G2 it becomes 6 move, but it's a similar story.
I know the wiring diagram, but it's not precisely the same, right?
It's a very good question, and it's so wiring diagram. So let me do it for maybe, Wiring diagrams are representation of permutation. You take the longest word, and then you consider a switch. So in wiring diagram, you have, you can have something like that, and then something like that, right? That's that. And so what you do, it actually corresponds to double wiring diagrams. You consider that wiring diagrams for positive part and negative part, and whenever you have such a switch, or such a crossing, you just replace it. So I'll just overlay it. You replace it with this. So it's one-to-one correspondence. You can receive.
But maybe picture more complicated. Maybe you need to draw. I don't know. For me, at least, it doesn't work the first transformation when you permute upper and lower. How you distinguish in this case when you replace to lower and when you replace to upper?
Well, so because we do pay attention to which reduced word we're talking about, right? So you have two reduced words. Well, so draw two wiring diagrams with different colors, and then one of them will correspond just to lower inclined edges, and another one will correspond just to upper inclined edges. Yeah, that's exactly how they do it in von Zelewinski.
I think for me the problem was a summation in this case.
Summation?
Summation. If you draw two crosses, like they. From the topological point of view, they cancel each other, right?
Yeah, but we
want to add.
Yeah, but we're talking about reduced words, so you will not have anything that cancel each other. This is a reduced word.
Only
reduced. Yeah,
so
this is all. Yeah. There is a similar theory, for example, so this is relevant for double Brea cells. There is similar theory for both Samuelson cells, and there you have to be more careful because you don't have to deal with reduced word. But here we're just talking about reduced words.
Thank you.
Yeah, but so it's a valid concern, but here it's not. It does not apply.
If it's not a reduced word, I guess you can use your identities for reducing.
Right, but question was about what you do with wiring diagrams in this case. Yeah.
So the theorem by Bernstein from Zelewinski was you choose any two reduced words,
right,
and any shuffle of these two words.
Yeah.
And then you have a diffeomorphism, and if you chose different words or different shuffles of these two words, it would be a different.
It will be different
diffeomorphism. And can I also get a diffeomorphism if instead of putting the diagonal at the beginning, I put it, let's say, at position 5?
Yeah, you can put it anywhere.
Okay.
Yeah, through using gauge transformation, and to get from one of those to intertwining operations can be realized by cluster mutations. Yes. Great.
Could you say again about how to get Jacob matrix? I missed the way about weight.
Oh, well, so weights. So we're here talking about shapes. Weights can be arbitrary. So if you have a picture like this, let me erase the unnecessary part. So all you have to see is that this matrix is tridiagonal, and if you look at it, you can, that's all you need. This is tridiagonal because from level I can get straight across I plus 1, I minus 1, but nowhere else, and that's why it's a Jacobian matrix. And then you can put any weights that you want.
Yeah, T plus and D and T minus. We can take all the time.
Right. Yeah, and then you can diagonal conjugate it to the way that Professor Tsujimada had so if you had here T plus T minus, it is diagonally equivalent to just having T plus T times T minus on all the inclined edges. So you can make it symmetric, you can make it Uni-Hessenberg, you can, Yeah.
Sorry, I missed the statement. So you had this thing that you said is related to the Stoda business, where you had this kind of thing. And what was the statement? So every 2 by 2 minor with what? Sorry.
So this is for diagram where you take kind of inverse of this diagram. Yes. So let me draw it again, so I can just draw it like this.
Yeah.
If you consider just say lower triangular part,
okay,
and consider all the minors which just live in the lower triangular part, all of them, starting from 2 by 2 minors, are equal to 0. Except
all minors.
All of them, yeah, because we only have one line going down, so there is no way to construct a non-intersecting family of paths.
But you also have the right side.
And the same is true for strictly right side. But in general, it's you have more.
So minors which only involve lower triangular or
exactly,
parts.
right. So in that sense, all of this have the same number of parameters, and in fact, they actually fit together to a single cluster structure that could be Q system structure or structure on rational functions, and that uses Hankel determinants. But that's kind of a separate story that I will mention tomorrow.
Are there any other questions? Okay, thank you, Misha. We'll come back a little bit earlier, so we have to be back here at 2:15.
2:15?
2:15.
Thank you.